So welcome, folks, to the third event in the Red Hat Research Days series. It's been a couple of excellent works being presented thus far and in an equally excellent way. And here's to us keeping that momentum going. So my name is Ahmed Sanaullah. I am a senior data scientist as part of the Red Hat research team, and I work on all things FPGA. And today I'll be your conversation lead. The topic that we are going to be discussing is programming, practical programming for FPGAs in the data center and on the edge. Before I introduce our speakers, I just want to give some context to this discussion. Over the past few years, we've seen that FPGA research has become increasingly critical, and there's a very good reason for it. You see, modern computing is this one giant paradox. On one hand, there is a need for specialization because in the post-Moore world, that's how you get performance and power performance. On the other hand, there's a need for flexibility because that's how you get to address a set of complex and diverse and dynamic workloads. And these two things are traditionally considered to be mutually exclusive. So how do you exist at the intersection of these two things? And as you may have guessed by the title of the talk, I am of course talking about FPGAs as the solution. And because for FPGAs, you can change the hardware, and that means you can customize the hardware to be specialized for a specific application. But at the same time, you have the flexibility to change that hardware so that you can adapt to changes in the workload or to target new workloads. And that just makes FPGAs ideal for addressing the growing demand for high-performance computing because, things like AI and ML mean that even your traditional non-HPC workloads suddenly have performance requirements that can't be met with traditional CPU computing. Then, of course, with all that data that we are currently producing, which we cannot process offline, that needs to be processed at the source, and FPGAs are a great way of doing real-time stream processing. And then at the edge, especially for applications and workloads that require some element of portability. In that sense, FPGAs can give you not just performance, but they can give you power performance. You can work within a power budget. Unfortunately, what we are still seeing is that CPUs are being used for workloads that we know that FPGAs are better at. And that is because FPGAs are so incredibly difficult to work with. The cost, the time, the effort, the expertise requirements, all of these mean that organizations don't find it a worthwhile investment. And we can't even upstream the support because forget the different vendors. Even FPGA families within the same vendor have so many differences. And so we need projects like this one here, which tries to address the performance, portability, programmability problem. What that means is that we want to get good performance for our custom hardware, but we don't want to spend months doing that, and we don't want lots of expertise. We want software developers, folks who have not had that much hardware development expertise to be able to, within timeframes comparable to software development, be able to get good designs up and running. And we don't want that we take our hundreds or thousands of applications that are critical and just rewrite the entire code for it to work on an FPGA. We want to have some element of portability between the different technologies. And so that's what's great about this project, and that's why we're having this discussion. So I'm going to stop monologuing here, and I'm going to introduce our highly experienced panel of speakers. Let me start with Professor Martin Herbordt, who is a professor of ECE at Boston University, where he directs the Computer Architecture and Automated Design Lab. He and his group have worked for many years in computer systems, and especially computer architecture and high-performance computing. More recently, their focus has been on system aspects of FPGAs in clouds and clusters. And full disclosure, he was also my PhD advisor. So welcome, Professor. It is great to have you with us today.
Well, thank you for, well, first, thank you for inviting me, and thank you for inviting me and Robert, and looking forward to this conversation. But let me, I have to be professorial here, and so let me sort of turn things around a little bit. As we've been talking, let's put the horse before the cart. So everything that you said about the post-Moore architecture is true and important. But rather than starting with programmable hardware, why don't we start with what we all care about here, and that is the data center. It's become increasingly clear in the last, well, 10, 15, whatever, many years, that communication is really slow and it's inhibiting solutions, the way that we can solve problems. So we'll go into the details of this later, but I wanted to bring up the idea of the smart wire. If we had a smart wire, so something where as the data passed through it, it could transform the data or combine the data or reduce the data, just imagine what sorts of things that we could do. And I heard something recently on one of the podcasts, a biology example, your spinal cord. We think, well, if you ever think about your spinal cord, that is, you think about it as being a nerve highway. But it turns out that it's actually a mini brain and is doing really sophisticated processing, and that's what enables fast reflexes and catching balls and other things like that. So anyway, to come back to programmable hardware, and I will get off the, I will let Robert talk in a minute, but to get back to programmable hardware, to make this work, that's why we need the programmable hardware, so not the other way around, and that is the history of it. Well, I'll stop there.
Very interesting analogy. I did not know that. So we're going to come back to that. But before that, I do want to introduce our second speaker, Robert Munafo. Robert is a third-year PhD student, also in the Computer Architecture and Automated Design Lab at Boston University. Robert designed his first general-purpose CPU architecture in 1979. Is that true, Robert? Yeah.
Mm-hmm.
Nice.
Yep. When he was 4 years old. Well, when he was 4 years old, that is.
That was a 4-bit processor.
Wow. And his first compiler in 1984, and he's revisited these types of work over the years. He was recently involved with the COPA project at Intel, which aims to standardize FPGA-based SmartNICs for widespread data center deployment. Welcome, Robert. It is great to have you with us as well.
Yes. Thank you, Ahmed. And full disclosure, Professor Herbordt is also my PhD advisor. So thank you, Ahmed. I am looking forward to this. This project is going to accomplish some new things, and I believe it has the potential to integrate sort of everyday non-hardware expert type programmer talent with reconfigurable hardware performance. And that's enough to look forward to. I think that's a lot.
Awesome.
Yep.
Okay, Professor, let's start with you. You mentioned in your intro that FPGAs enable intelligent network fabrics. That's really cool, but we know that computer architects love to come up with the solution first and then the problem. Is that the case there? And if so, what is the problem?
Oh, yes, our Achilles heel, yes. No, actually, we did start with a problem this time. I think I've already jumped ahead and given a lot of what I wanted to talk about here. Communication just takes a long time, tens of thousands of cycles, hundreds of thousands, millions of cycles of CPU cycles to get data across. And that really changes the character of what you can do. Well, let's think, if communication were infinitely fast, then the smart fabric that you talked about would be the CPUs themselves, but it's not. And so if we want to have a smart fabric, well, we have to build it ourselves. And I think at this point, I did bring, I did prepare some slides here. And so maybe, Ahmed, you can pull up the first one.
Let me see. Let's see. Is this the one?
Yeah, that's the one. And so yes, the spinal cord is another brain. And but as I already mentioned, the spinal cord, our compute in the network, so to speak, is able to process and control complex functions. And so I mentioned ball catching or tennis playing. You couldn't do any of those things without having well, maybe you'd call it an IoT processor. I prefer the network processor. If you go to the next slide, please. So this is an example from low latency trading. So people who do low latency trading have known about this for a long time. There's nothing like vast amounts of money to inspire innovation. And so in this example from Arista, you have trading actually occurring in the switch, and that shaves, well, entire microseconds off the process so that you don't have to go to the server, but you actually perform the trade in the router itself. So I think I'll pause here.
Very interesting. But, so you've talked about in the spinal cord and the brain, and you've talked about low latency trading and Arista routers. I guess what I want to ask next is, what about something that's more relevant to the audience here, which is real data centers and the everyday applications that they support?
Yeah, well, I think that as our audience, I think, knows a lot more about this than at least Robert and I do, and that is that the sorts of applications that would be amenable to this kind of processing. And so I was hoping that, Ahmed, maybe you could type this question into the chat, and we could get some responses. But while you're doing that, let me take a shot. And I think the first point, and this is from this point is an interesting one from a Google paper maybe 10 years ago, where they made the really nice observation that until the data center, you had no hope of doing this at all. It's hard to think of before the data center, there was the internet, and the internet is old and stodgy, but it's we're almost there now. So because we're in a data center, we can assume a number of things. One is that we can engineer low latency delays, at least in the hardware. Another is that we can have relatively homogeneous equipment, of course, being modified over, year by year. And then we have a single administrative entity that can modify protocols and influence the hardware features. So just having predictable low latency is a possibility or tractable. But you ask what kind of applications, and I think that there are maybe three kinds. And the first is what we've already talked about, applications that just need low latency, like high performance computing and low latency trading. And of course, in machine learning, training is helped by having low latency. A second kind we've also hinted at, and that's the smart wire. So if you can transform data as on the fly, like in compression or encryption, that's also really good. A third kind, I'll plug now some research, HPC-oriented research that we're doing, and that is that you move data around in HPC because it needs to be with other data, and that is to combine it in some way. If you can do that in the switch, then you have, you've really improved the application. But I wanted to also talk about something that you generally don't think about when you think about if you go this far into the problem. And maybe that's the most important thing of all. And that's what, again, to shift a little bit, that's what the Department of Energy thought about maybe 6 years ago when they hired Intel in the COPA project. So the Department of Energy cares about really large data centers and making them cost effective, something that we're all interested in here. And they were thinking that if we could do a lot of compression and smart networking, then we could get rid of most of the network, or at least a lot of the network. We could reduce the number of switches, wiring, floor space, cooling, all the data center things. So anyway.
No, it's interesting that you mentioned smart NICs, because when we, and I think this was in someone's response in the chat as well, that when we think of FPGA as the data center, the most common term we hear is SmartNICs. But that's not true, is it? There are other ways that we can put an FPGA in the data center, right?
Oh, well, of course. I remember a really nice picture from your dissertation on it that I think I'm going to ask you to describe now. I think you called this FPGAs everywhere in the data center. Now, of course, we know that that's not on every node, and every type of node is not the same, but I think you should talk about this for a minute.
Is it in the slide deck?
I hope so.
Let me see. Oh, there we go. Yeah, I remember this. Let me pull this up. Yeah, I'm going to preface this by saying this is not comprehensive. This was what I could find in the research that I was doing at that time. But I'll just go over this really quickly. So, you have, you can put FPGAs in a lot of places. You can put them within the switch, and this would be more of a centralized deployment for network packet processing. But then you can put FPGAs in different places within a data center node. You could put it between the network and everything else in the data center node, which we call the bump in the wire. You could hook it up to the CPU in a traditional coprocessor sense. You could even have these FPGAs talk to other FPGAs directly. And this could be, within the same node or between nodes for ultra low latency communication. You could provision FPGAs as an independent resource from the CPU. You could put the FPGA between the storage and the CPU to accelerate memory operations. And then there's the SmartNIC FPGA. So now looking at this, actually I have a question that gets asked a lot. Why an FPGA? I mean, for example, look at the coprocessor FPGA. Look at what it's going to be doing. I mean, we have GPUs, we have ASICs like the tensor processing unit that can also be complexity offload engines. So wouldn't that be better?
Well, it could be, and sometimes it is. So if you have just one application or three applications, and especially if that application has sort of vast marketability like machine learning, then something like the TPU is ideal. And also there's widespread use of encryption chips and probably lots of other things that I don't know about. But there is a problem with the ASICs, and that of course is that they are good for a single application, and especially if that application doesn't change very much. There are also GPUs are of course possible, but GPUs are missing something. If GPUs had networking support of the kind that FPGAs do, in other words, if a GPU had a number of networking ports that would stream directly into the processing elements and directly back out again, then perhaps they would be more useful as network processors, but they don't. Neither do CPUs. Maybe you could pull up the next slide. Now, at this point, maybe I'll talk a little bit about FPGAs and what I mean. So the first point is that most of FPGAs are not configurable at all. FPGAs have tens of thousands of ASICs embedded in them. Those ASICs are compute units and memories, and especially in our context, network ports. If you take a look at this picture, you'll see that as I have there, it looks a lot like a GPU. It has block RAMs, which are kind of like shared memories. There's thousands of them, like you would have at least dozens or hundreds of shared memories in a GPU. You have pipelines. There are differences. Those pipelines are customizable. That's the configurability. The connections are customizability. But why don't you go to the next slide, please? But here is the key idea, and that is that those pipelines, call them CUDA cores if you want, or FUDA cores for FPGA cores, they can talk not just to their own shared memories or block RAMs, but they can talk to the network ports. And there are maybe 100 of them on a current contemporary FPGA, and those are all at 100 gigabits per second, or a lot of them are at 100 gigabits per second. It's really, that's what FPGAs are. They're really network processors.
Sounds good. That's awesome. But the impression that I got from what you said is that FPGAs are like GPUs, but with better network interfaces. So theoretically, if I could add better network interfaces to GPU, then I would not need an FPGA anymore. But that leads to the question then, what about the reconfigurability aspect of hardware? Isn't that important as well?
Yeah, well, everything that you said about post-Moore's architecture is true and important, but let's stay. Why don't you put the slide back on again, Ahmed? I know we're trying hard not to make this a slideshow, and we won't. We promise. But I'm going to stick with this for a minute. If you have 100 gigabit interfaces going directly into your compute unit, just imagine how efficient that needs to be to make it worth doing, not to have most of that be air. And so that's one reason that this has to be configurable. Another is because applications change a lot. Protocols change all the time. It's this co-design between protocols and hardware that has made FPGAs, at least at the high end, what they are, this family of network processors.
Very interesting, very interesting. So this naturally leads to this question that all this incredible flexibility that we're getting, all the benefits that we're getting, this must come at a cost. I mean, when you're giving developers all these extra knobs that they have to tune, all these features that they have to specify, wouldn't that make programming hardware different and, quite honestly, more difficult than programming software?
It sure is, but let's start by, well, I think, why don't you move to the next slide on that? So what I wanted to talk about, here was, I think it's good to get into programmability, and that's where we are. But to talk about programmability, we have to have an idea of how you program an FPGA. So we're not going to teach Verilog here, or even OpenCL for FPGAs, but I do want to give a sense of what goes through the head of an FPGA designer when she or he is designing software or configuring an FPGA. And the primary or the overarching idea of that is that of space, of spatial computing. So in the CPU, you write code, and so this is from one of our favorite applications, which is molecular dynamics. On the right side, you see some equations that we're implementing, and in a few minutes, you could write some lines of code that implement those equations. You write those same lines, and it really takes no longer on an FPGA to do this, but you end up with hardware. And you'll see that there, instead of having sort of statements, you have, you have physical units that have been laid out. So why don't you go to the next slide, please? So one of the interesting things, and this is an example that I also want to bring up later when we talk about the difficulty of, or the problems of getting efficiency when you program an FPGA. And that is that not all of these units are created equal, and not all of them have the same rates of throughput. So in this example, we have streams of data coming from particle cache and being filtered, and the filtering takes out most of the data. And you can imagine this also happening in a database application, where most of the responses are getting filtered out and then being sent on for further processing, those that are remaining. And that's exactly the software, the paradigm that we're using here. But once we've done that, so we've replicated one, but not replicated the other, and then for efficiency, we want to replicate this as much as we can across the chip. And if that works, if we have filled up the chip with parallel units, we've maximized our parallelism, we've also maximized our performance. And, well, as I said, to bring it back, this is kind of the idea, the programmer's model. This is how when we sit down with a problem, kind of our starting point, before we even write code usually.
Awesome, awesome. Robert, you've been quiet for a while, so I'm gonna switch over to you, and I wanna ask you the same question. Why is FPGA programming so hard?
Right. Okay. I actually don't mind having the professor go first because this is how we learn, and this is how most hardware. This is how most hardware people learned about FPGAs, is that they see the illustrations of the potential, all those connections, and it does seem a little overwhelming. It's, Professor Herbordt has said this already by contrasting spatial programming with sequential. So I think of it in somewhat different words. So just hear me out. I think that FPGA has sort of a hardware language, a natural hardware language, which is an overwhelmingly parallel language. And that's what I think of when I think of Verilog. We have hardware design languages, which are called HDLs, and Verilog is the language they taught me when I was in school learning how to do hardware. So a normal software program, I would have, just programming a normal CPU type program, I would have, let's say, 10,000 lines of code, and they're in a sequence, and the program is going to just do one thing at a time. And I call that sequential imperative programming. This is pretty common terminology. You've probably heard it. But in hardware, imagine that all 10,000 lines, you write a program, but all 10,000 lines of code are running simultaneously, and they're all going to react to each other continuously and instantly, because this is how circuits work. Circuits could have millions of elements. They're always active all the time. They're always instantly reacting to each other. And in order to manifest the potential of circuits, there's a language that lets you do that. Well, how can you possibly use a language with that type of power? How can a person who learned computer programming, sequential, step-by-step type programming, how can a person like me learn how to coordinate those 10,000 simultaneous actions so that something coherent and useful actually results, like some kind of computation that somebody would want to have happen? Well, that would be Verilog, and Verilog is hard to program. But we also have HLS languages, and this problem doesn't exist in HLS languages.
By HLS, I'm assuming you mean high-level synthesis, yes?
Yes.
Yeah. Well, let me take this one. Let me pick up from where Robert left off, and I think it's time for a tutorial. So let's please bear with me, and I think that we have, say, 3 minutes on what high-level synthesis. Well, first, just how programs map to hardware. So if you can go back to the slides, please.
So which one?
The one that's the one that has the syntax tree on it.
Okay, found it.
So let's remind ourselves how software gets compiled. So I think most of you had a course at some point where you learned about translators, and so the statement gets compiled into a syntax tree and then into some other structure that allows some optimizations, and then into tuples, and then finally into code. So let's next slide, please. So in the upper left-hand corner, we have some code that does this simple arithmetic operation. And I don't have the syntax tree here, but it's you can imagine it's the same one that we have, or something similar to what we just had. But let's see what happens to it. Well, those operations, instead of getting mapped to instructions, get mapped to, let's call them virtual operations or virtual hardware elements. We have a virtual multiply and then 2 virtual adds. And then those virtual elements get mapped onto real time. They get mapped onto clock cycles. And the first 2 can get done in a single clock cycle. That's how long they take. And so that's why they're appended as they are. In the next phase, down at the bottom, those get mapped to real actual hardware, in this case, the DSP unit and the add subunit within an FPGA. So next slide, please. So I meant to say, so this also illustrates the spatial nature of the programming at a much lower level, a lower level than we usually think, even as spatial hardware programmers. This is usually just a black box when we program. But anyway, so we want to convert this from a single operation, which is pretty useless, into a stream. And the example now has a for loop and some number of operations, some number of times through, and an input and an output array. And we can see that the example is now a little bit more complicated. We have data coming in and going out, and a state machine, and the state machine is applying the operations. And so I think that hopefully you find this reasonably straightforward. The operations get mapped onto cycles, and the data flows through them. And this is sort of the basics. I also wanted to make a comment about just the performance of this. It's really bad. This is a really terrible design. As you know, as well, I say we probably not all hardware people here, but as even a beginner hardware engineer knows, when you have a pipeline, that pipeline should be full. And this pipeline isn't. It's empty most of the time. And that gets us, that use of time, that use of efficiency of the pipeline is probably the single biggest killer of hardware performance that we face, and the single biggest problem with HLS, that HLS systems face.
But shouldn't this be easy to optimize it? It's so obvious.
Yeah. So just as basic block compilation is a well understood problem for compilers, so this is for hardware synthesis. But let's take this to the next example. And could you give us the next slide, please? So we're back to old homework, because this is another one of Ahmed's projects, or this was actually one that he didn't start, but that he cleaned up in the end, as we'll get to. So here we have that example again that I was talking about having the multiple filters going into a single force pipeline, and the arbitration logic for hardware designers is pretty easy. I mean, not easy in hours, but easy certainly in a small number of days, complete with debugging and operation. Next slide, please. And so on the right side, that was what we got from high-level synthesis, from the Intel OpenCL compiler. And you'll notice that there are explicit acknowledgement operations, explicit handshaking, and also explicit use of data channels, which is an Intel OpenCL construct. So this all makes sense, but the performance is really terrible. We got about a factor of 100 slowdown. Now that's not, a factor of 100 slowdown. And when we dug into it, we found that this handshaking was so abstruse and so dense that almost never were actual data transfers happening. So why you go to the next slide? But not to go into this in too much depth, I'll just show on the right side, this is what Ahmed came up with, that he found a way to code the OpenCL to take the arbitration completely out of the circuit. And here we got pretty good performance, but it completely defeated the whole purpose of using high-level synthesis, which was to start with some software code and just have the compiler figure all this stuff out on its own.
Yeah, well, this brings back nightmares. I wouldn't say memories. So Robert, your turn. Why don't you share with your thoughts on high-level synthesis compilers and how do they work?
Okay, sure. I want to get you away from your nightmare very quickly. So the HLS compiler, it's really like a CPU compiler, at least the way I look at it, and they definitely all start that way. So you have an HLS compiler is like GCC or Clang, the compilers you're familiar with. They start with instructions that are written in sequence, just normal sequential programming. The instructions that they're given, it might be a C function, has an expectation, which is that the sequence is strictly defined. Often the program will decide its own sequence, but the sequence is strictly defined by the program. The compiler needs to be faithful to that sequence, but they also need to adapt the program to the capabilities of the actual hardware. And this happens on real, this has been happening with real CPU compilers forever. So that's no different. But machines might also have, although machines have limitations, so the machine might not have floating point, but machines also have possibilities. A machine might have massively parallel floating point. They might have the potential for improved performance, for parallelism of various kinds that are not directly expressible in that original language. However, there are many well-researched methods, such as loop unrolling or compute unit replication, where the compiler can exploit those capabilities. And the compiler has to be able to do that, but make it as if the program was doing what it was originally, as if it were executing sequentially.
And what do you think is the biggest challenge or limitation in this process?
Yeah, so again, this is kind of like what we've been saying is, you remember the millions of elements instantly simultaneously reacting to each other, right? There's no way to do that in normal CPU language, unless you write a program that emulates a circuit, or there are other models like huge grids of automata, things that nobody actually uses in the real world. And in any case, if that was your program emulating a circuit, well, it's still hard to understand the circuit. It's still hard to understand how to orchestrate the circuit. So you don't really get anywhere by doing that. So to achieve the result that we need, the compiler needs to strictly preserve the semantics, which means to make sure the result always matches what the CPU would produce as if it had actually done it sequentially. So there are some notable exceptions to having to actually do things sequentially. If you have provably independent calculations in a loop, that means you have implicit parallelism that can be exploited. The researchers and the companies that came out with tools for doing something like OpenCL for FPGA from Intel. I'm sorry, we're not picking on them, but I happen to have background in that. They provide something called a single work item kernel. It takes a single loop in a program, usually a loop that scans an array for input. It has an array for output, so they can turn those into streamed input and output. And the loop calculations become a data flow pipeline. This is just what we saw in the illustrations that were just being shown to us in the Vitis example from Professor's slides. So that's one example, single work item kernel. You can also do an ND range kernel. This is a lot of compute units. So we have compute unit replication. This is with each with their own data pipeline. So this is like GPU or CUDA programming for those who are familiar with that. There is a need for high bandwidth memory for things like coalescing memory accesses. The memory controller usually has to be pretty sophisticated. That is not given to you. You have to find some way of handling that or implementing it, dealing with that. Putting the arbitrator outside the channels was one example of dealing with that. It's a lot of work. Loop unrolling as applied to hardware, that typically also increases the memory bandwidth that you end up needing to have. Compute unit replication, I think I just said that. So I think I have addressed your question, hopefully.
So the impression that I'm getting here, and because you've not told me otherwise, it seems like you're trying to use the CPU compiler to generate hardware. And Professor Martin just said a few minutes back that the programming model is incredibly different between hardware and software. So how can you use a CPU compiler to describe hardware?
Well, so yeah, so I'm not. I want to point out I'm not aspiring to reach that. So there's this thing called the Pareto point or Pareto optimal point between GPUs and ASICs. We're not trying to do that. So the specialized applications, the specialized hardware design, that's not what we're trying to do from a CPU program. Instead, we're targeting the majority of programmers. And, well, Ahmed discovered, and while he was still at school with me doing the thesis, maybe he'll tell us about this. I think it was pretty cool. He was working with the Intel OpenCL tools. He discovered that the programs can be adapted to the compiler that was provided to him once he worked out what the compiler can do. And once he worked out how to make the program amenable to that compiler's expectations, so to speak. So maybe Ahmed will tell us a little bit more about that. There's sort of, with knowledge of the compiler, he was able to get things to go a lot better. We're trying to address the same users, but now we're saying, well, what if we can change the compiler? What if we're not stuck with a single particular specific version of, this particular type of FPGA tool? Well, with the open source compiler GCC, we can modify the compiler's own inner workings. There are quite a lot of research in the pass ordering problem, the optimization ordering problem, the selecting what optimization is to do, pass selection problem. There's a lot of research using machine learning to harness, deal with the many possibilities that there are, and the fact that you kind of need to decide lots of things all at once. So machine learning is good for that. A lot of research there. The research pretty much only addresses CPU. There are very tiny couple of exceptions to that, but we are trying to cross-compile for FPGA. So we do have some new issues in this project to address. You can't simply run the program on your laptop to find out how fast it will run on an FPGA. So we have to handle that. But yeah, that's why I see it has potential.
So I'm sorry, Professor.
No, I think.
Go ahead.
I was going to skip ahead. I think we're a little bit behind time. What we had thought where we would be here. So I think that we skip ahead a little bit. And I did want to make one point to amplify or to summarize what Robert was talking about, and that is that this project is really ambitious. That there's been a vast amount of effort put into this, and I think that it would be nice to give an explanation of why we think that we could possibly succeed. And for this, I will again turn it over to Ahmed, who, as part of his dissertation work, kind of had a proof of concept for, as I said, I've prepared a slide or two, which you can use or not. But anyway, I think this is the time for us to hear from our moderator again.
Well, let's see. So I'll be very brief about this because we are running short time, and I do want to get to this GCC part that Robert's talking about. So this was a few years back when we did the initial experiments with OpenCL, and we found we were getting terrible performance. So we did some experiments to try and figure out why that was the case. And this is something that I call, and I know I call it technically incorrectly, a manual fuzzing, whereas basically what I was doing was giving the compiler a bunch of input programs, and then I hacked the compiler bits so I didn't have to generate the full hardware, and I could just look at the circuit that I was outputting. And for 2 months, all I did was just trace wires, write a program, generate the output, trace wires. And just to give you some context, there's about a few million wires to trace. I mean, not that many. But we got some very interesting observations out of it. What we saw was that the reason why we get terrible performance is not that just the compiler is bad or the programmer needs more expertise. It's because there's both of them. They're doing something that they shouldn't be doing, or in the compiler sense, something that it should be doing, but it isn't. So what do I mean by that? We were expecting the compiler to be doing certain code transformations, like automatically unrolling a loop. It was a very basic one, but it wasn't doing that. On the other hand, as a programmer, we were thinking, if we specify code in a certain way, we could get really nice hardware. That wasn't happening. And even some of these were stuff that we were picking up from the best practices guide. And what was going on was that by specifying ourselves certain hardware patterns, we were actually constraining the compiler, and it was not giving us the right amount of parallelism. And so we found out that if you apply a systematic series of code transformations, you can actually unlock the compiler and you can really get some good hardware results. And so I'm seeing Professor put in this summary slide, so let me pull that up. This is basically what we got. When we have these existing ad hoc tuning designs where you spend months and months tuning your HLS code, and you only got within one order of magnitude of the reference HDL design, but by using these very simple 6 sets of transformations, you can get very close to Verilog, and this was great. But there's a problem with this. There's a big problem, and that is that nobody's going to spend another 2 months to repeat the entire process if something in the compiler changes, because if something changes, this whole thing breaks. And so basically I needed to graduate, by the way. That was the most important motivation. I couldn't graduate on this project alone. So I went back, and this time I said, well, instead of looking at a circuit, can I look at the intermediate representation? Can I extract enough information to figure out what's going on? And well, intermediate representation is not a circuit, so I need some context. And to do that, I came up with this notion of an FPGA model, where I can look at code fragments and I can use them to estimate how good or bad my hardware quality will be. And then I wrote this profiler that could then search the input intermediate representation code and find out how many of these code structures existed and to what degree. And then to test this, I wrote a bunch of probes, I call them. They're basically small functions, and each function really tested one aspect of the model. Putting all this together, we were able to look at specifically what the compiler could and couldn't do when it came to generating hardware. And then we got some very interesting results. So what we saw was that you could, all the things that we did in the optimizations, those certainly made sense. That's the things that the compiler either wasn't doing or was doing. But then we also saw something even more interesting, that there's a gray area in between, where there were things that the compiler was doing, but not doing well. And that's what the best practices guide was saying, really. It was saying you should do this because it was supposed to work well. And it did work, just not well. So at that point is where I left the project, and I think Robert took over there.
So at this point, so I'm going to go organizational again. So at this point, I think that we should talk about the project. So, but let me just summarize. So Ahmed did, it was really a tour de force, and at the end of that, I thought that we had solved the problem. But as Ahmed also said, we're still a ways away. We're still outside the compiler. It's still in some way auto-tuning. And so what we've been, why don't we go to Robert, excuse me, we're going to skip some of the things we had planned on you talking about here, and we'll give you the last word to talk about our progress. But let me give a quick overview of the project. So if we go to the first block diagram. So is that the first one?
No, hold on.
The first one has like just 2 boxes on it.
Yeah, it's okay. We can go to that one if you want.
Okay.
Yeah. So this is what Robert was talking about, and it's already pretty amazing that that Robert has hacked GCC, found the optimization controller, and as Oli suggested, Oli Drepper suggested, found that this is indeed modular and modifiable, and we have we're trying this stuff out. Next slide, please. So let's add a little bit of detail. So we're not just looking at the input code, but of course we're starting with something more abstract, in this case the syntax graph, and we're not outputting code yet, we're outputting another intermediate form. Next slide. But what we'd really like to do is machine learning, and so this is how we envisage inference happening, that we have a trained inference engine, and it takes the graph dump and as input, does inference, figures out for the program what a good set of optimizations should be, and sends those back to GCC. Now, of course, the inference engine is going to have different formats than the syntax tree and the optimization sequence, and so there are a few transformations that have to happen, encodings and decodings. Next slide. And there's a big problem. GCC does not generate hardware. And so our idea is, and Robert claims that this is not that bad, our idea is that we append a hardware generator. But the current open source hardware generators are LLVM based, which means that we're going to convert the GCC intermediate representation into an LLVM intermediate representation. And at that point, this is pretty much it for the forward pass. Next slide. In order to do training, we need vast amounts of data, the canonical problem. There are not that many programs that we can use, so we need a generator. We need a generator. We'll start off with training libraries, and then, well, Robert will talk a little bit about this in a minute. Next slide. Another big problem is that the dirty little, or dirty, not secret, but little secret of all of hardware is that it takes forever to compile, hours longer. We can't wait for hours for each test case. We want to get them done several times a second or faster. So we need a fast evaluator. And finally, probably not in the first phase, but eventually we would also like to make this hardware dependent or hardware specific, as well as application specific. And so that's the final piece to our project. So at this point, I think maybe in the last few minutes that we talk before we open it to general discussion, maybe Robert can talk about a few of his favorite problems. There are many and obvious problems, but maybe Robert can select just a few that you'd like to talk about.
So, Ahmed, oh, I'm sorry. Yeah. Okay, so Ahmed had a nightmare. I have a nightmare too. So the nightmare that I have. So R&D in general. This is the nightmare. Is you're in a PhD program. You've got this idea. Maybe someday you'll succeed in having your thesis be well
approved.
Yeah. It's kind of like a job interview. So it's this tension. Am I gonna get the job? So research. R&D work in general, you don't know how it's going to succeed until you do it. So there's this big question mark. It's like I'm looking through the fog. I don't know where I'm going. So that's one nightmare. We have plenty of ideas. We have faith. And it'll work out. But so that's one thing. Just a general, high level idea of research is unpredictable. Okay. So there is a lot of published compiler work. We have a lot of ideas that we get from people who've done things already. We have to adapt it to FPGA. We've been talking about that. So that's great. More specifically, a more specific nightmare, I guess, so to speak, is that machine learning models, they have famous problems like overfitting. I haven't done a machine learning course. I know there's a lot of math. I've never tuned a new model, so how do you deal with overfitting? It's like a new problem every time you encounter it. It has to be, each new model needs to be solved a different way. Apply an old model to a new problem, you still have to tune it so it doesn't overfit on the new problem. So there's that. All right. But the nightmares, are not the only thing that dominates my thoughts. We have open source. We have the open source way. So Red Hat is on board with us with this. We have this idea that we can take community efforts and combine together with other people in academia, with other people in the community at large. Some of the people listening here perhaps want to accomplish similar results. We want it to all be something people can trust, something people can look at and say, I know how this works. I know how this works so well that I can see something where the possibility for improvement. And so that's the golden ray of sunshine in my dream that keeps me going. The fact that we're not doing this alone in the dark tunnel, so to speak.
Robert, could you tell us? Oh, there's a big echo happening. Oh, never mind. I'll walk through. I'll power through it. So, Robert, could you tell us a bit more details about these pieces here? For example, one of the things that's really interesting to me here is the Inference Engine and really the inputs and the outputs to it.
How
are you setting up this model there?
Yeah, sure. So this, although I might not know how models work inside, so this is a common task everyone's going to have to do. Usually machine learning models take input in some kind of standard format, like I call it a stereotyped format. It might be, say, a vector, 100 numbers from 0 to 1, that type of thing. But a C program is not 100 numbers from 0 to 1. It's an arbitrarily long number of symbols. And one of the problems of a C program is if you change even one character in your C program, it'll change what the program does. And the model might care about that. The model might need to know that they changed this one character. So there is an arbitrary amount of information in the C program, but you're trying to squeeze it into a fixed length number of inputs. So, information theory, Claude Shannon says maybe you can't do that. So there might be the encoder might be a little difficult, and we need to look at there are a lot of examples of how this has been done. We have a few ideas for ourselves, but there's definitely the need to convert data from one type of representation space to another. On the output side, same thing. The model will tell the compiler what compilation optimizations to do and in what order. Again, the model is not going to output that. It's going to output some numbers from 0 to 1, which then have to be expanded out into a sequence of steps that are like names, So again, that's a encoding or decoding, I guess you might call it, problem. So that's what the encoder and decoder are that are closest to the red box on the slide, the encoded and optimization sequence boxes.
And Robert, could you tell me more about the GCC to LLVM converter?
Yeah, okay, so that's the box in the upper right corner. So let's see, I'm glad you kept the slide on the screen. Hardware generation in the lower right, like you said, usually it's, I'm not sure if Ahmed said it or Professor Herbordt said it, but they've been LLVM based, or they've been completely closed source, but the ones that we can access are LLVM based. Well, it's fortunate that GCC and LLVM are both designed by groups of people who know how to do compilers, and one of the common things they have in common is that they use an intermediate representation. At some point in the process of compiling the code, it's in something called static single assignment form. And this is where most of the optimizations that we care about actually take place. And static single assignment in GCC is not the same as in LLVM, but they're close enough that they can be translated. But the thing is, if you've got this hardware synthesis tool, this open source HCL tool in the bottom right corner, that has its own, has all of its own structure. There's not just a bare software subroutine or function that's in that blue box that's going to generate hardware. It has I call it a framework. I don't mean a software library, but there's extra information around it that it's using to keep track of what it's doing. We can't generate all of that ourselves. But what we can do is we can feed the same function into both. So we can give the same software function to the existing open source tool, give the function to GCC. And we stop them both at the point where they're in SSA form. And we can extract the contents of the function as it was compiled and optimized by GCC and glue it into or paste it into or transplant it into the place where that function code is in the HDL generator. And because SSA has a certain calling conventions, as long as you have the same function arguments in the same order, the function SSA guarantees the function will still perform the calculation that you want it to. So then the HDL generator can just go ahead and proceed using this code that has been optimized by our clever optimizer.
So I think we're almost out of time for this initial part of the session. So I'm just going to ask you one last question there. So because it seems to me that you're not doing supervised learning. So, and that means that your evaluator needs to be, it's absolutely critical for that evaluator to be practical and successful in what it's supposed to do. So could you share some thoughts about that?
Yeah, so Ahmed, you inspired us on this. You've developed some methods to do evaluation of your own. We're adapting some of those. We have similar methods that are being used in a lot of the other research that's been done for CPU. You can look at the SSA. You can see how much instruction level parallelism is possible. You can see how many branch decisions does it need to make every time through a loop. Combine lots of numbers like that, statistical measurements, they're sometimes called feature extraction, can be used to estimate how well the loop will perform. You need to find out how many times the loop will run. That can often be done by compiling the program and running it on a CPU and using a profiler. So there are good ways to estimate performance, and that's what we're going to do to speed it up. The HDL tool also gives us one important bit of information, and it can figure this out quickly. It doesn't have to do the hours and hours worth of thing that it usually does. That's called the initiation interval, the number of clock cycles between each successive piece of data feeding into the beginning of a pipeline. That's figured out by the time of the second slide that Professor Herbordt showed with the pipeline. By the time they get that far, they know what the initiation interval is going to be. So we will use that.
Awesome. Well, folks, this has been a really interesting conversation, but I think we're going to wrap it up and open the floor to questions. But before I do that, I want to get one last comment from both of our speakers. So, Professor, if you want to go first.
Yes. Well, thank you. This has been awesome. I think that I did have a comment that I was going to summarize, but we're a little bit late, so I think I'll skip that and just thank you very much and look forward to questions. I've already started to answer them in the chat and look forward to continuing that. Thank you.
Robert?
Professor the Moon Lady, he's typing in the chat while he's doing the presentation. Well, that's funny. Oh, I see that. Yeah, that's great. Okay, so yeah, thank you. I won't say much either, but I appreciate it again. I feel we're going to appreciate the opportunity to be able to share what I'm doing with all you folks. Like I said before, it's a great opportunity that we have to empower programmers who are sort of like everyday programmers to use this hardware that is everywhere in the data center and not have it fall flat just because the compiler can't figure out what it's doing, basically. So, yeah, thanks.
Awesome. Thank you, Professor. Thank you, Robert. So we're going to start taking questions. Now, you could put the questions in the Q&A section. You can put them in the chat as well. We might miss them if they're in two separate places, but you can certainly do that. And you're very welcome to even join us on stage and ask us questions or give comments or even have a roundtable discussion. So let's go have a look at the Q&A in the chat to see if there's any questions. So there was a question that came up very early.
Ahmed, you can remove the slide.
Oh yeah, let's see.
And we can see more people. Yeah.
Yeah. So there's a question that came up earlier. Let's see. It was So it was from E.G. Nathan. I'm sorry if I'm mispronouncing the last name. It was they were asking for some insights into how FPGAs can advance modeling of quantum circuits and quantum computing simulations, and their ability to address error corrections.
Oh goodness, Robert, have you thought about that at all?
Well, so I do know a bit about quantum simulation. One of the benchmarks that GCC infamously was able to optimize, parallelize in the spec suite was a simulation of one of the quantum algorithms for factoring prime numbers. I don't think that's relevant, but quantum computing simulation, it's a CPU pretending to be a quantum computer. So you have to consider all the possibilities, all the 2 to the nth possibilities that n qubits of data have. So it's a massively parallel thing. It can be parallelized. The actual wording of the question, Professor. Go ahead.
Yeah, let me take this a little bit. So one of the reasons I got into FPGAs is because sometimes there's a hardware solution where there's no software solution. Now, of course, you can always transform one into the other and vice versa. But one thing that you can do in an FPGA is support fan out. In other words, you can do a broadcast. And now, if the broadcast is to 10,000 elements, it might take a few cycles, and you have to, no, you don't have to, but the tools will build an amplifier tree or the equivalent of an amplifier tree. And that's where I think the power will come in FPGA as opposed to CPU or even GPU simulation of quantum circuits. The analog properties of FPGAs.
So the fact that you can put analog circuit elements into the FPGA.
Yeah, what I'm thinking. So
we might have
when I think about a fan out of more than 4, I think that's no longer digital. That's analog. So if you have a fan out of 10,000. That's something that the FPGA, the compiler, and the hardware will give you, and it's done efficiently.
Yep. So there you go, massively parallel.
Yeah, I don't have any insight about error corrections, except that also can be done extremely efficiently.
Oh, that's right. You asked about error correction. Yeah. I took a quantum computing course. I kind of figured that we would simulate the errors, with, stochastically. There's got to be better approaches to that can be done in hardware as well.
There was a question on virtualization in FPGAs and partial reconfiguration. So. How do I phrase this? Well, what is the impact of, one, does the support exist? 2, what are the limitations of it? And 3, what steps how can it improve this performance, programmability, and portability problem?
Yeah.
I guess it's three pieces to that question.
You know, I think the last one will just make it really miserable and hard. I think that my take on it, and again, this is shooting completely from the hip. My take on it is that this is another thing that you want to do with an FPGA, and it's a good thing to do with an FPGA, but it's something that is harder than what we're talking about, which was doing a single application. I think that we talk about virtualization a lot when we have our meetings, and the methods so far are still pretty crude. The things that you share, that you virtual. So what I'm thinking about is kind of like in the cloud, if you have a shared resource and you want to have multiple users share the resource. Because of the spatial mapping or the spatial compute model, you have to have physical regions, or these are the ways that people are viable nowadays. Of course, anything's possible, but you have predefined how big the segments are, and the applications have to drop into them. And that's a lot of overhead. And so who's saying in our meetings that this is still rarely done in the cloud right now?
Yeah, when we're talking about the Amazon implementation of the other Red Hat sponsored project that we're doing in our lab.
So where virtual circuits is really good is for software. I mean, it is really good, and for something like software-defined radio, where you're swapping out protocols, that's perfect. And so that's a real application with a real use. But I think for virtualization in the data center, it's I think it's orthogonal to what we're talking about. Why don't I put it that way? I think Aaron Smith at the bottom had some completely relevant questions. If you want to hop down there, not to skip anybody, but that's the ones that I saw, and I know that those are things that are.
Aaron Smith mentions that he worked on a similar thing in his dissertation.
Oh yeah, so I've met Aaron at I think I don't remember the last time, but I think in Paris once we were speakers together in a session, and but anyway, if we look back, one is why GCC instead of LLVM, which I tried to answer, but I think Uli and Ahmed and Robert both have better takes than I do.
Yeah, why GCC and LLVM? But we're part of the GCC culture, I think. We have expertise that's been very, very closely involved with GCC for a long time, with working for Red Hat, and so it's just easier to be able to ask questions and get answers on it. You know, GCC's been around longer. It's much more integrated with the open source movement over the long term. There's Richard Stallman right there behind me. Different reasons to use GCC, you know.
And well, I'm trying to, go ahead.
Yeah, so I had a question. This goes back to figure 7. Let me pull that up, actually. So I'm looking at this figure, and one thing that I'm noticing is that the hardware part, the FPGA part, doesn't come till, the GCC LLVM convert, or not even that, till the HDL generator. Like the really FPGA specific part. So my question is, do you think this approach can be portable and work for CPUs and GPUs and not just FPGAs?
Yeah, maybe Robert has done a vast amount of reading hundreds of papers on this and getting a background. And, and I'm sorry that we missed Aaron's work, but maybe I think that the very, very short answer is that it's already been done, that there are papers that apply machine learning in ways that vaguely look like this. But maybe Robert can expand on that a little bit.
So I want to start by trying just copying the models and hyperparameters of some of the papers that were developed. I'm pretty sure that because our feedback, remember this is unsupervised learning, so there is an evaluator that provides the feedback during training. since the feedback will feedback different numbers, it's going to have to learn different things. And because the input we're generating is different, we're going to be training it to learn how to optimize different base of possible programs. So, you know, we might end up having to use a different model and tune it differently. Also, it's been suggested to us that a lot of that research is kind of out of date, and we want to develop new things. We're not just going to copy old, you know, what old people have done. There are new possibilities now that every year there is like 2 or 3 new paradigms for how to do machine learning. Do you remember when dropout was a brand new thing? You know, do you remember when recurrent neural networks were a brand new thing? Those aren't very old by my standards, but, you know, new stuff keeps going up. So, not sure have I answered your question with regards to that. Silence. I take that as a yes.
I see that Aaron has joined us on video, so welcome.
Aaron, yeah, you have sound. Go ahead.
Can you hear me?
Yes.
I can hear you, Aaron. Yep.
This is awesome. This is great to see a lot of this work continuing. This was a long time ago, though, when FPGAs were just starting to take off, like in the mid-90s, that area there. There was a lot of research done, a lot of conferences available at that time. And a lot of focus was on how you use something like a GCC to do the translation into a hardware language. And what the group that I worked in, we basically took GCC at that time and modified it, like I think you've done as well. I mean, it makes all the internal data structures available. So the data flow graphs, all the control flow graphs, and everything that you can generate from the internals, and then apply all the keyhole optimizations that you need. So what you're doing is you're going one step beyond what, or many steps actually beyond, where we were able to go, in that we had a specific machine target for which looked similar to RTL, right? And we would target that. So we would generate our finite state machine, generate our data path, tie them together, and it looked like RTL, right? And then we would take that RTL and generate, at the time we had a VHDL compiler. Mm-hmm. And that VHDL compiler was provided by Xilinx. I don't know if we can say companies and stuff.
No, but yeah, sure. And we said Intel like 18 times. So
yeah, okay. So what we actually got, was I think there were people at the time talking about doing the feedback loop that you were doing. And I think the craze at that time was, as you mentioned, neural networks. But I think, anything along that lines is good. And that's the missing piece from all the stuff that we had done. But it's interesting. So we were targeting back then Xilinx 4010, which, very small devices, right?
Sure, yeah.
So we built a piece of hardware that had a RISC processor and 3 FPGAs all on the same CPU bus, so that you could, it was like 2 cycles to get things in and out. And that was our sort of research on how well we could get that to function. And so we targeted things like compression, like lossy JPEG compression, DES encryption, Markov model. The whole thing was funded by Markov model programming, Markov model training for speech recognition, which was a thing back then.
Yeah.
So, we were able to speed up the Markov model training by a factor of 100, which meant, we could, something that took for weeks and weeks after we had everybody's speech in, took hours, which really, we were heroes for the other group. So, but it's great to see that this work is continuing forward.
So that's great. Yeah, this type of work transforms through the decades. The And so you remember the day when the part number, the Xilinx part number, actually told you how many logic modules were in the chip. So that's 1985. That's when they started. So back in the time that it was possible to do your project, the memory was just as fast as the internal register bus in the CPU. So because the memory speed ratio has changed, there's all these new sort of paradigms for how to do hardware acceleration and how to integrate the two types of processing with each other. So that introduces new things. We have the benefit, though, you had to have GCC a lot more than we have, because GCC now has plugins that let you look at the internal data structures and dump extra information. It already has a dump feature that will dump the data trees, the intermediate representation stuff. That's such a common demand for that they made that a part of GCC without even using a plugin. And of course, we're adding the ability to reorder the passes, which hitherto did not exist in GCC, although it had been hacked into it from time to time by other people. So it's great.
Things change.
Yeah. We're doing the same thing. It's the same spirit. I feel like Intel's doing the same thing they were doing in the 70s. They're just
All are. I mean, that's that's the thing. I mean, computer design basically reached its peak at the CDC 6000. So,
but the rules keep changing every year. You've got to learn new stuff, and that's what we're doing. Yeah.
No, but I love that when we so our research group, I emphasize this to the new students, that there are no new ideas. There are just, you have to find them and put them together in new and creative ways, and do good engineering. And of course there are there are on occasion really great ideas, but mostly there's great stuff happening with old ideas.
Nothing wrong with that. That's how we improve. So
that's right. And there's so many ways to combine the ideas together that I still have the nightmare wondering how am I going to accomplish it. Yeah. Half joking there. Yeah.
Yes, I did say. Oh, so Heidi said, did I say FUDA cores?
I definitely said FUDA cores.
I am going to go into this for a minute, because this is an alternate approach. So I've been fighting with FPGAs only for 20 years, or even less than that, about 18 years. I've been doing this seriously, which is only the second half of my, I'm sorry, giving away my age there. So
it's only half the history of configurable hardware.
So my take on, I talk quite a bit about spatial programming, and that's really a thing. I'm into that, and the reason is when I talk with my students or my peers who happen to be my students, like Robert, when we think about things, we use my whiteboard, and we draw up applications and figure. Well, anyway, we do everything on the whiteboard. It's all blocks and arrows. And then I'm not a competent VHDL programmer, so then the people in the lab who are competent VHDL programmers translate that, and usually in a small amount of time. We translate the blocks and arrows into code, and now debugging and synthesis, that takes more time, but the actual creation is really straightforward once we have the design. And so my idea was always that why don't we just modify CUDA so that you can do generalized blocks and arrows? And we even had a name for that, FUDA. Now it turns out that somebody else has used FUDA, and that is to translate CUDA into an FPGA, which is a terrible idea. Because you are, terrible idea by intuition, and also Ahmed proved that was terrible in his results, that if you constrain OpenCL or CUDA to have work items, you're not making it easier, you're making it harder for the compiler to do its job. So anyway, I think that the FUDA idea has two really important directions, one of which has been demonstrated to not be a good idea, and that's CUDA directly to FPGA. And the other, where the jury is out, I still think it's a good idea. The maxillary compiler looks a bit like what I'm talking. That's Oscar Menser's company, and very, very fine work, also going back more than 20 years. His Stanford dissertation was on FPGA compilers. So anyway, so those are two takes on FUDA. One is something that looks like CUDA, but it's really for FPGAs. That might work. But anyway, we have tried an alternate approach, and that is just take something even simpler, which is C code and machine learning in GCC.
So I just wanted to add a little bit on the end there. I do dream of having the custom language that's good for expressing all the stuff you can do in hardware. That's certainly an approach that's been researched a lot as well. And they never go anywhere. Everyone makes their own paper about their own language, well, a couple of them get, reused again 1 or 2 times. But anyway, so our approach, we're doing something where you can take standard CPU programs and compile and run them. That's a different thing that has different potential, different possibilities. Right, Professor?
Yes.
Yeah.
Yes.
Yeah.
Yeah, no, I'm parallel processing. I'm also scrolling through the questions.
Oh, yes, of course. You're checking.
We have a new question. How do you think the devices NVIDIA is working on that combine GPUs and smart NICs compared to FPGAs? Different use cases or less performant?
Yes, we've been dying to get our hands on one of those, and one of my collaborators, Professor Shellam in Tennessee, actually has a couple. And if they are so one thing is we love FPGAs for all the reasons that we've been saying, but we don't work for Xilinx or Intel or Altera or AMD. We are researchers. And I know Red Hat has exactly the same idea, completely non-denominational. If GPUs can do these functions, then we are really interested in them in the same application. We're interested in GPUs anyway, but if they have the capability that I was talking about, and that is the direct streaming and better support for that, then yes, indeed, they would take part of the FPGA niche or niche, take part of the FPGA niche of compute in the network. Yeah, it's something that we're looking forward to trying out.
There's going to be a scenario where you have certain applications that will run better on the GPU smart NIC, and there are certain workloads that will run better on the FPGA smart NIC. And then there's also the DPUs, which have neither GPU nor FPGA, but rather have this ASIC on it.
Yeah, these are things that we talk about a lot. One thing that I will one thing I'll toss out and just go really high level, and that is that FPGAs FPGAs look a lot like GPUs. They have they have tens of thousands of floating point elements in them. So do GPUs. GPUs have configurable elements. If you see one of Professor Dali's talks, you'll see a lot of things in his projected architectures that look really FPGA-like. Lots of network connections, lots of flexibility in getting from in the communication networks, all stuff that is way beyond where the designs were 10 years ago. So I think I've kind of punted on the question, but it depends on where the devices go and what their capabilities are. But again, there's nothing that is particular in what we're talking about to a particular product. It's just the state of where we are right now.
Awesome. So we're going to take one last question because we're almost out of time here. So this was asked before, but I think this is worth. Why do part of the work in GCC and then translate and continue in LLVM? Why not just do it all in LLVM client?
Well, I don't know. I thought I said I like GCC because I have experts I can ask questions about GCC from.
Yeah, we have not managed. We have not managed to get. I think Oli was on the talk a little bit before, and we have not persuaded him to get on stage with us and give an answer. So no pressure there.
No pressure. But just we've got. We had a choice. We've got LOVM. It's brand new. We've got lots of knowledge about GCC. I personally have much more familiarity with GCC over 30 years of usage compared to LOVM. So it's a personal preference as well.
Yeah, and I think that I don't, since I haven't looked at it personally, I don't, but I have heard that the optimization, what do we want? How do we put it? The optimization fabric, to use a completely meaningless word, is richer in GCC.
Yeah, I definitely believe that. I think LOVM was a little bit behind GCC for a while. They had to catch up with graphite. They had to catch up with some of the aggressively, massively parallelization stuff that GCC does. Yes, I don't know, but I'm probably a little biased there.
So I think we're almost out of time. So thank you, Professor. Thank you, Robert. This was wonderful. And please join us for the next event in the Red Hat Research Day series.